Okay. Okay, just speak up.
Okay. We would like to continue. Next, I would like to introduce Shen Zebang, and he's a postdoctoral researcher at ETH Zurich with a research focus on an entropy-informed approach for PDE solving. And yes, the stage is yours.
Hello everyone. My name is Zebang Shen. I'm currently a postdoc at ETH Zurich, and I'm in the OD group hosted by Professor Niao He. And it is my pleasure to present our work, Entropy-dissipation informed neural network for McKean-Vlasov type PDE. This is a joint work with Professor Zhenfu Wang from Peking University. So let me first give you a very brief summary of the presentation. So basically, we propose a neural network-based solver for the McKean-Vlasov equation with singular interaction kernels that emit strong guarantees of error estimation. Don't worry if you are not familiar with the keywords of McKean-Vlasov equation, singular interaction kernels, and the error estimation. We will introduce them in this presentation. Okay, so let's first introduce the McKean-Vlasov equation. So in the McKean-Vlasov equation, given a known initial distribution rho 0, the time evolution of variable density rho tx is determined by three terms: the drifting term, the interaction term, and the diffusion term. So here we take the drifting term to be determined by some gradient field, gradient V, where V is some known potential. And we can extend this to general vector field, but let's say we focus on this gradient field special case. And the interaction term is used to model the interparticle interaction, And since we're considering the mean field limit regime, so this interaction between particles can actually be captured by this convolution of some interaction kernel K with our current variable density rho. And lastly, we have the diffusion term, which is used to model the random collision between particles. So in the previous slides, we have introduced the McKean-Vlasov equation in its macroscopic view. And to better understand the meaning of this dynamics, let's consider this microscopic view. So let's consider a stochastic process xt, where the xt equals to minus gradient v xt dt plus k convolve rho at txt and plus Brownian motion term. So here, the law of this stochastic process at time t is actually the evolution of this law is governed by the McKean-Vlasov equation that we showed in the previous slides. Okay, now that we have introduced the McKean-Vlasov equation, let's consider some special instance of the interaction kernel, which is singular and of great importance. So the first interaction kernel that we'll consider is the Coulomb interaction kernel, where K is given by minus gradient G, and the G is given in this form. If you are familiar with the Poisson equation, you know that G is the green function of the Poisson equation. So basically, given the input is the Dirac function at the origin. So this type of interaction, so here I'm specifically focusing on the repulsive case. We can also for the attraction case, it's more complicated, so we will discuss that in the future. Okay, so we can see that K is singular in the sense that when X goes to 0, K blows up, it goes to infinity. So another important example of the singular interaction kernel is the Biot-Savart kernel. So if we plug in the Biot-Savart kernel into the McKean-Vlasov equation that we previously see, it gives us the vorticity formulation of the 2D Navier-Stokes equation. And here, K is given in this way, which is a scaled version of X perpendicular divided by the square norm of X. A special property of K is that it is divergence free. And also we can see that K k tends to infinity when x goes to 0. Okay, so about error estimation, the goal of this talk is to provide a uniform in time control over the distance of some hypothesis solution to the ground truth. So let rho theta be a trajectory of probability distributions parameterized by theta. The goal of this presentation is to design some potential function of theta such that there exists some constant c that is independent of theta, so that we can have a uniform in time control of the KL divergence between this hypothesis solution and the true solution. Basically, we want to have for any time in this given time interval from 0 to capital T for this inequality to hold. Okay, so this is here's the outline of this presentation. So we will first introduce the high-level idea of our approach, and then we will present the error estimations of the various equations that we considered, which is the main theoretical contribution of this project. We will then discuss how to implement the proposed approach numerically, and present some preliminary experiments result to show the effectiveness of the proposed approach. We will then discuss the limitation and some future work. Okay, so it is known that the Laplacian operator can be equals to the divergence of the gradient. So the diffusion term on the right hand side can actually be rewritten in this way, which is a divergence of rho times gradient log rho. Here we use the log trick. And if we move the right hand side, the term on the right hand side to the left, we actually obtain an equivalent formulation for the McKean-Vlasov equation, which is a continuity equation. Where for this continuity equation, the velocity field is given by A of rho. So A is some operator which, when takes in some input, when takes as input a distribution, it gives you a velocity field. What's important about the continuity equation is that it preserves mass. And so now, as long as we know how to move the mass around, and if the velocity field that we are using to move the mass is exactly the velocity field of the McKean-Vlasov equation, we will be able to recover the solution to the McKean-Vlasov equation by solving this continuity equation. Now the problem is that we don't know this velocity field A of rho. Okay. So the idea of this paper is to introduce a hypothesis velocity field F. So given this hypothesis velocity field F, we can define the hypothesis solution via this continuity equation. So here we assume that the initial distribution is null, and here rho f0x equals to rho 0x. Okay. So to recover the McKean-Vlasov equation, let's try to write it in a much similar form as the McKean-Vlasov equation, except that since now I'm not exactly using the velocity field of the McKean-Vlasov equation, there will be some error term. So basically, let's define delta f to be in this form. So the hypothesis solution, the continuity corresponding to the hypothesis solution, can actually be written in this perturbation form, where A rho, it's the same operator as the McKean-Vlasov equation, but now we don't know the solution to the McKean-Vlasov equation. We only have this hypothesis solution. So we plug in rho f in A. Okay, so now that we have this perturbation view, a very straightforward idea would be to do a stability study. So if we pick a proper Lyapunov function D, some discrepancy measure between the hypothesis solution rho tf and the rho t, and if we are managed to show that the time derivative of this discrepancy measure is controlled by some upper bound, some function of f, let's say it is called RTF, and then if we integrate over time from 0 to capital T, we have successfully managed to establish this uniform in time control of the distance of rho tf to rho. So in this paper, we will consider the potential function rho f in this form. which is the time integration of the weighted L2 norm of this perturbation. And here the weight is exactly given by the hypothesis solution. And I abused the notation a little bit. So if we parameterize the hypothesis velocity field by f theta, then we use r theta to denote our f theta. Okay, so we will now introduce the error estimations that we have obtained for various equations. We will do this from easy equations in an easy to hard manner. So first we'll consider the special case of the McKean-Vlasov equation where there is no interaction. So this degenerates to the Fokker-Planck equation. We will then consider the case where there is indeed interaction, but this interaction is bounded. So it's regular, which means that you can expect we obtain the desired results easily, not easily, without much effort. And I'd like to mention that we can also handle the case where this interaction kernel is linearly bounded in the sense that when the kx is bounded by some constant times x, the norm of x, when the norm of x is sufficiently large. We will then consider a more difficult case where there are singular interactions. So I will briefly touch the Biot-Savart kernel case, but will not go into the detail of this one because it requires a quite different analysis technique. Instead, I will focus on the Coulomb case. So let's first take a look at the Fokker-Planck equation. So basically, it is the McKean-Vlasov equation without interaction, which is given in this form, and apparently this is a linear PDE. So you should expect that it is not difficult to solve. So here, if we pick the Lyapunov function d to be the KL divergence of rho tf and rho t, we would have that for any time t, we can calculate the time derivative of KL between rho tf and rho t. Then we arrive at this very nice equality here. And the first term is a negative term and is usually known as the Fisher information. And the second term, which is the weighted inner product of rho tf and a gradient log term. To handle the first term is nice, and to handle the second term, you can easily use the geometric arithmetic inequality, mean inequality to arrive here. And if we simply drop the negative term, we would arrive at the estimation that we would want to achieve. So by integrating over time, we obtain this uniform control of the KL divergence for the Fokker-Planck equation. Okay. So this is easy because we have no interaction kernel. What if we do have interaction kernel? But let's say for now that it's regular in the sense that it's bounded. Okay. Let's pick the Lyapunov function as the KL divergence again. And let's compute the time derivative of KL between rho tf and rho t. Again, we have this very nice equation where in the first term gives us the Fisher information. The second term is more complicated. It's the weighted inner product of K convolves rho tf minus rho t times some gradient log term. And the last term is the one that we had for the Fokker-Planck equation as well. So following the same idea, we can handle the last term easily by using this the geometric arithmetic mean inequality. And now the problem is that how do we handle the second term? So now that we have assumed that K is bounded, it's actually easy. So let's use the geometric arithmetic mean inequality again. And the first term can actually be controlled by the Fisher information, the negative Fisher information that we have in the previous inequality. And to handle the second term, we can exploit the boundedness of K. So we can pull out the L infinity norm of K. Then we end up at the L1 norm of rho tf minus rho t. And then use the Pinsker's inequality, you obtain KL type bound of the last quantity. So we arrive in this estimation. So this estimation is good in the sense that we can use the Gromov-Waltz inequality to transform it into the type of control that we want. So basically, we would have this type of estimation, which fits the purpose of error estimation of this paper. Okay, so I will briefly discuss the result for the 2D Navier-Stokes equation. So here, the interaction kernel is the singular Biot-Savart kernel, and we actually obtain a better result compared to the bounded kernel. Okay, bounded kernel case. It is better in the sense that it is still uniform in time, and the constant before this EIN potential RF is actually independent of T. Of course, we would require additional assumptions. So basically, we would consider the case where the initial distribution rho 0 is sufficiently regular, and that the spatial integration domain, which I have been purposely on purpose avoided, should be the 2D torus, which is basically a box with periodic boundary condition. I try to avoid this integration. I try to avoid this integration domain to simplify the presentation. And the reason why we are able to achieve this nice result is because K, the Biot-Savart kernel, is divergence free, and it's actually can be written as the divergence of some matrix field. And importantly, this matrix field is bounded, which would allow us to obtain such a nice result. But I will not discuss the details of this result. Okay, now I will focus on the Coulomb case, which actually better fits the logic that I presented before. So for this Coulomb case, simply picking the Lyapunov function to be the KL divergence is not enough. We will need to introduce additional terms in the Lyapunov function. So here we introduce this concept of modulated energy, which is proposed by Savati in 2020. So this modulated energy is defined to be the integration of gx minus y of rho tf minus rho tx and rho tf minus rho ty. And the Lyapunov function that we'll pick to derive the target as error estimation is the modulated free energy. Basically, it's the combination of the KL divergence and the modulated energy. So this energy has been is used in Bresch et al. In 2019 to establish certain mean field limit result. Okay, so now let's pick the Lyapunov function to be the modulated free energy. And the good thing is that again, we have this very nice equality. Basically, the time derivative of this modulated free energy between rho tf and rho t admits this very nice form where the first term is negative, so it can help you to cancel certain terms. And the second term is the weighted inner product of the perturbation delta. Sorry, this should be delta tf, and this additional term that appears in the first term. Okay.
So the screen switch up. Okay, sorry. I think it's like the new power saving. So it's switching off and then went off.
You have a little message saying the balance should go.
Okay.
Should I press the turn on button?
Yeah. Oh, yeah. Turn on button.
Okay.
Very good. Okay. Yeah, sorry.
Oh.
I think it's logical to
So how do I return to the? Okay.
yeah.
Okay, cool.
Sorry.
Cool. So in this equality, we have that for the second term, we can use the symmetric as before to pull out a term that we want, and another term, the positive term, can be cancelled by the first term. And now the problem becomes, how do we handle the last term? Okay, so now we need to exploit the property of the Coulomb interaction. So recall that at the beginning of the talk, I've mentioned that G is actually the green function of the Poisson equation. So basically, it satisfies this equation. And now the first thing I want to do is to show that part of the integrand in the last term is actually of a divergence form. So first, let's use the definition of the Poisson equation. So rho t minus rho tf minus rho t actually equals to gradient g convolves rho t minus rho tf minus rho t because of the Poisson equation. Also, sorry, there's a negative sign there. But because there is also a negative sign in the definition of K, so these two negative sign cancels, and we have the first equality. And because we know that the Laplacian operator is actually the divergence of the gradient, so we can equivalently write the first term as the divergence of gradient g convolves rho t minus rho t, rho tf minus rho t. And now let's use this the following identity. So for a vector field, we know that the divergence of the vector field times itself is actually of a divergence form. It's a divergence of a matrix field. So if we use this identity, we arrive. We have shown that this term is of a nice divergence form. Okay, so now that we have shown this term is of this nice divergence form, the natural idea will be to use the integration by part to handle the last term that we're trying to handle. Okay, so let's do integration by part, and we arrive. We obtain the first equation, and since here, okay, so here we need to make the additional assumption that the velocity field that corresponds to the true McKean-Vlasov equation is Lipschitz continuous. Under this assumption, we can pull out a term of the L infinity norm of gradient of A applied on rho t, and we obtain this first inequality. And since this L2 norm of gradient g convolve rho tf minus rho t is actually the inner product of gradient g convolve rho t minus rho t times itself, you can do integration by part again to obtain this the second equation. And now that we have for the last term of this equation, we can exploit that g is a green function, and therefore we would using the Poisson equation again to obtain the third equation. And now that we obtain this one, the modulated energy pops up, right? So we can, yeah, this gives us the last identity. Okay, so now that we have established this bound for the last term that we're trying to bound, then you can just use in the Grunwald inequality to bound the modulated free energy in a uniform in time way. And since KL is contained in this modulated free energy, it is also bounded. So for this McKean-Vlasov equation with Coulomb interaction kernel, we also managed to establish this error estimation. Okay, and now let's discuss a bit about how to numerically implement the proposed the approach that we proposed. Okay, so first, the first thing that we would want to do is to let's compute the how do we compute the value of this EIN potential. So this is actually easy by noticing that this EIN potential admits this expectation form. So let XTF be the flow map defined by this ODE. The xt equals to f t xt dt. Okay, so if you're not familiar with the flow map, here's a definition, which when you plug in xt, it should give you xt as output. And if we the hypothesis solution rho tf can actually be written as the push forward map, so the push forward measure of xtf applied on rho 0. And here is a definition of this EIN potential. And if we use the change of variable formula of the push forward measure, we obtain the second equality. And if we just use the definition of the flow map, we obtain the result that we want. So here I changed the order of integration of d and dx0. Okay, so now that we have this very nice expectation form, how do we compute? Sorry, how do we compute this pairwise loss inside? If we have additional interaction term, it requires a more elaborated discussion. But now let's focus on the very special case where we do not have interaction term. We only consider this Fock-Planck. Let's consider the Fock-Planck equation for now. So here, the only unknown term is the gradient, is this score function, right? Gradient log rho tf. And luckily, we only need this quantity along the characteristic curve. So along this characteristic flow, we can actually have we can actually have this the time derivative of this score term in a closed form, and everything on the right hand side is known. Therefore, and additionally, since we assume that we know the initial distribution, you can actually sample x0 from row 0 and evolve from 0 to t to calculate this score function. Okay. So, which means that we are able to compute this pathwise loss, and using Monte Carlo's approach, we can sample a bunch of x0 and take the average, which gives us a pretty high accurate estimation of the EIN potential. And so once we have this way to compute the EIN potential, one application would be that, okay, let's have any hypothesis velocity field, right? Any hypothesis solution, let's plug in here in this EIN potential. Since we have the error estimation, basically this provides you a way, a general way of quality quantification of any hypothesis solution. Okay, the next task would be that, okay, let's say I parameterize the velocity, the hypothesis velocity field f with f theta. So basically the goal is that I want to use this EIN potential as a loss function to train my neural network. So by minimizing this quantity, I hope that the neural network, the output of the neural network actually fits, can recover in some sense the true velocity field, and then I can use that to recover the solution to the McKean-Vlasov equation. So here I abuse the notation a little bit, where I use r theta x0 to denote r f theta of x0. And in order to, so for the purpose of training a neural network, what we need is the way to compute a stochastic gradient of this quantity. And to do so, we would use a very well-known approach called a adjoining method, which was developed for PD constraint optimization problem. But now we can write r theta x0 in this standard OD constraint form, and then we can use the adjoining method to compute the gradient. Okay, I will not go into the details of this one. And okay, yes. And now let's see some experiments of our project. Okay, so in order to establish, right, to access the quality of the output solution, we deliberately pick dynamics such that you know exactly the solution to the true McKean-Vlasov equation. The true solution to the McKean-Vlasov equation. And here for the 2D Navier-Stokes equation, we pick this Lamb-Olszyn kernel because for that we exactly know the solution to the Navier-Stokes equation. So we compare with three methods, which the first one is physically informed neural network, which is short for which is abbreviated as PIN. And the second one is our approach, and the last one is called a deep random vortex neural network, which is also another method to propose to solve the 2D Navier-Stokes equation using neural network. So in the first plot, we show that for all these three included methods, the training loss is reduced over a long training period. So if other methods fail to achieve a very good result, it's not because they are undertrained, it's because the loss function may not be appropriate. So then in the second and the last plots, we show the accuracy of the proposed approach significantly outperforms the other included baselines. Okay. And we do the same thing for the McKean-Vlasov equation with the Coulomb interaction. So we pick this Baron-Blatt profile where if you initialize the distribution as a uniform distribution over an L2 ball, then the solution to the McKean-Vlasov equation will remain as a uniform distribution over an L2 ball, but the radius of this ball will grow over time. And we can use this to assess the quality of our solution. And we observe a similar phenomenon. Okay, now that we have introduced our approach and show its efficiency in terms of solving at least a certain class of PDEs, what are the limitations of our work and what can we do in the future? So first thing is that the equations that I have presented are all in the overdamped region. So basically it's a first order kinetic, first order system. What if we consider the kinetic region, right? For example, the kinetic Fokker-Planck equation or the Vlasov-Poisson equation. So our current result shows that if the interaction kernel in the kinetic region, if the interaction kernel is linearly bounded, we can establish similar type control. Or if the interaction kernel is singular, which is exactly the Coulomb interaction kernel. But if we make the additional assumption that for the velocity variable, it has a monokinetic initialization, then we can establish similar result. So for that one is known as the Euler-Poisson equation. So what about the boundary condition? I have deliberately avoided the discussion of that in the presentation. So for now, we are only able to handle the unbounded case or the periodic boundary case, because in our work we extensively used the technique of integration by parts. For these two cases, you can show for the unbounded case, you just need to make some diminishing property, diminishing assumption. For the periodic boundary case, the additional term in the integration by part automatically vanishes. But ideally, we should be able to handle other boundary conditions like Newman boundary condition or dirichlet boundary condition. Yeah. Also, what if we have the additional source term in the PDEs? So right now, we are writing everything in the continuity equation, so mass is preserved. But if we have additional source term, the mass is no longer preserved. And therefore, the current parameterization may not work. And we need to think about how to fix that. So finally, what about other PDEs, right? Ideally, we would cover as many PDEs as possible. So we tried the similar approach on the Proximity equation, but we couldn't figure out in terms of the theoretical proof. But empirically, it works well. And also, another nice thing to have would be cover this very important Landau equation. I mean, we're also able to do it numerically, but I guess to establish the similar type of error estimation is quite difficult. Okay, thank you, everyone.
Thank you very much for the talk. Are there any questions to Shen Zebang?
Can you show your the error estimate result where you show that the result is independent of the unrelated?
Okay.
Yeah, I'll be confused with the statements that the constancy, yes, independent of the unrelated. In the sense that to what fix the unrelated here or
Sorry?
to what fix the unrelated?
You mean you can pick any time, capital T.
Real.
So what do you mean? Sorry.
So why the constant C here can be
Okay, so here by assuming the integration domain is torus, and assuming the initial distribution is good, we can actually establish certain log Sobolev inequality. And you can imagine that, okay, let's say it's here. Let's say if you have some, okay, if you consider this estimation, right? If you have log Sobolev inequality, you would have additional negative term that would allow you to have a uniform, to remove the dependence of the constant over time t. Yeah, because of we use some log Sobolev inequality there. Thanks.
There was another question. Yeah.
I'm trying to use the log Sobolev to get a new combination
estimate in the world of the or the marché and the list.
For which equation?
You know,
Yeah, that's what we do. That's what we do.
probably you said it and I missed it. I'm sorry.
Yeah.
Okay, if there's no more question, then let's think again.
Recording first.